Okay, before I start my presentation, I just want to summarize. I just want to give you a background about the work, how we started and all. See, this is actually a kind of, the collaborative work with the Sidra Medical Center, where one of the research scientists called Nagarajan Kathiresan, along with there is another professor from TU Delft, from Amsterdam. We put together jointly, kind of, activity. Maybe we started around around 6 months ago, and as part of that, I was actually providing all kinds of hardware and connectivities and kind of help support for this paper as well as the presentation. And unfortunately, Mr. Nagarajan could not make a trip here to present. On behalf of him, I'm actually representing here. Just want to tell you the background of this. But this is actually a kind of good work the team made. It's a kind of the global collaboration kind of stuff from India, Qatar, and one in Amsterdam, kind of stuff.
Delft is not Amsterdam. Okay.
Pardon?
Delft.
Oh, Netherlands. Right. Okay. Sorry. Oh yeah, the professors, the part-time professors also here actually from Delft. Actually, thanks. So. By the way, the system is also from ULIC research lab. This is where we got the system to do this activity. The BW, this is actually mostly on a porting, porting the x86 based application, the open source application on the Power 8 based hardware. It's not Power 9 though. This is 6 months back it happened, but we are looking to do that on Power 9 too, the same implementation. So the topic what I'm going to cover here is actually just talk about the next generation sequencing, and then the mapping, the exact the BWAKIT pipelines, and also what are the activities we did as part of the porting, and what are all the verification we did as part of the porting. And this is the thing I'm going to talk about it for the next 20 minutes. So we all know that because of the Moore's law as well as there are a lot of improvement happened in the embedded system for genome sequencing, and you see that here in 2013 the automated capillary spending around $100 million, and as we speak now the Illumina X10 it's a product actually from US, and around 2015 we are spending around 10K to 1K money for per genome, and this is actually the trend is like the cost per genome is actually decreasing, the price drops continuously, and at the same time we also see a trend where the genome the machines producing a lot of data because a lot of research happened, and because of that the huge data it is producing. And that is a challenge we are going to have. If the data grows, we have to have a good kind of the system as well as kind of the method to process the data. That's the thing I'm going to talk about. See here, the next generation sequential computational pipelines. This is a process it does sequencing machine generate to produce a DNA data. And then the read will happen, and then the mapping to a reference genome, and then it will get sorted, cleaned, and location also get adjusted, and then finally we get we get to find the mutation expressions rate as part of that. And the important activity here is actually the results from x86 as well as the Power 8, whatever we produce has to be the same, and that also we verified as part of this. And especially Mr. Nagarajan predominantly works on this area, so he has done the right work on that too. He is actually the domain expert too on that. And then we all know that GATK best practices pipeline, and this is actually essentially used for the cancer diagnostics. And then these are the following steps. The BWA read pipe mapping, and then Picard sorting and mark duplicate reads, and then Indel realignment, locally realigned reads, and then base recalibration, and then variant calling. And these are all the process, it will go through when you do that. And what we have seen here is most of the time, it took is actually in the mapping side only. That's what here you see, the 40% on mapping, and then the remaining time like sorting 20%, and then all other activities, it includes another 40%. And this is where there are a lot of work we need to put together, and that's why there is an open source tool which we picked up, and ported it on Power 8 system. And the overview of this gives an overview of the BWAKIT, and it has got like the 4 the open source applications. These are all available in the GitHub. You all must be knowing about that. SAM tools and Trim-a-Dap and the PWAMM and SAM Blaster, and these are all executed one after other in the fashion described here. And this is part of the thing, and later on we build a standard index of BAM, and then we do the genome mapping. And as part of that, these are the applications from the GitHub where we picked up, and the team worked on porting the application on Power. And we have a detailed the paper also how we did it, and what all the experiences we had while doing the porting also we documented that. And yeah, this is a place where we have already published the complete paper on that, the BWAKIT port PDF, Sidra.pdf, and you can take a look at it when you want to know more about it. And then I don't need to tell you about this. The Power 8 system was the one we used for doing this experimentation, and and also the system we got access from ULIT Research Lab, and it was actually just running only one system, and this is the configuration that the lab provided, and we also this is the important thing here, the ROD reads, and the whole human genome is 400 GB uncompressed, and there is a reference data available also which we published it too. And yeah, as part of the benchmarking on OpenPOWER, we did these the procedures, like kind of a usual benchmarking steps we followed, running the steps to do that. And the performance metrics used for benchmarking, and also the results what we are seeing here. This is a little important here. See a number of when we did it with one core, the time it took is actually 134 minutes. But when it is actually when the core was getting into 80, 537, but after that we are not seeing much good performance also.
So this is not core, this is hardware threads.
Yeah, hardware threads. Sorry, yeah, number of hardware threads here. Sorry, yeah. So
this is actually quite good, because you still get for a quite large number of threads, unlike you.
Yeah, you even get for 4 hyper threads, they still get an improvement.
But your 4 threads are the same as the 8 threads.
what is that?
The 8 threads on the Power 8 are equivalent to the 4 threads you get on the Power. The core on the Power 9 is the Power 8 splitting 2.
Yeah, but this is Power 8.
Power 8.
Yeah.
Yeah, so you should get linear speed up. Well, they get linear speed up to 40, which is pretty.
Yeah, up to 40, but after that it is
Basic.
going. That's what the study also says that we should not use more number of threads there. Like a limited number of threads we have used. In summary, we have that actually, and this is the plot of whatever the data we got, and we all know this. And the validation, this is also another important, the whatever we, after the mapping, whatever the results, we compared with the x86 results to the Power 8, and those are all, equal. And that means, we did not lose any data or anything, and all, everything, went well as part of the porting, and also the results. And this is what I would say, like, kind of a success, and on a Power 8 machine. But now we want to move on to the Power 9 and see how well it performs, and what are all the things. What are all the results we get that we are looking forward to do it. So as part of the summary, successfully we ported, and also the similar results we got it on Power 8 compared to the x86 box, and there are like the architectural alignment also, like we have made, and those are all rightly worked, and the scalability of BWA support for large number of cores in Intel and OpenPOWER architectures. That means it's better to work with the limited number of the threads, like thread per core thing. Any questions?
Thank the speaker.